I guess before we get started, I'm sorry that there's no music today. I forgot to credit last week on Tuesday, the music that we played was also by music created by a 16A student and their band, Mint Julep, I believe. But again, if you want to have music played before class, please send us your original creations because we are not allowed to play any kind of copyrighted music. And are we at time? Okay, we have one. If there's a question from last lecture, I'll take it in a minute if anyone has anything before we officially start. Okay, well, let's get started with lecture then. We're now officially in Module 3. It's the second lecture of Module 3, and today we're going to continue talking about the locationing example that we started last time, and we're going to build up to try and understand more parts of the example. So remember last time we said that there were two parts to the locationing example, right? First, when you had all of these beacons, you had to figure out a way to get the distances from each of the beacons. And then, after that, you had to figure out a way to combine the measurements to actually, figure out where your location is. So remember we were thinking about trying to find ourselves on Earth using locations of different satellites and using our distances from the different satellites, right? That is the GPS problem that we set up last time. And then we went on to say, well, let's first focus on the first part of this problem. The first part of this problem is actually figuring out, well, how far away am I from satellite 1? Or how far away am I from satellite 2? The example that we were looking at in class was thinking about, let's say our beacons are at the Campanile and Corey Hall and Soda Hall, and we wanted to figure out what this distance is reliably. So the way we did that, or we introduced this idea of correlation to be able to actually understand and compute how far away we are. And why were we thinking about correlation? We were thinking about sending these periodic signals, right? We had this transmitted signal, and then there was a received signal, and there was a shift or a delay between when the transmitted signal was actually received. And based on this delay, we were then going to say, well, if I know how much time it took for the signal to get from the satellite to me, and I know the speed at which the signal was traveling, in the case of an electromagnetic wave, that would be the speed of light. In the case of an acoustic wave, which is what you'll be doing in lab, it'll be the speed of sound. If you know that speed, you can then figure out the distance between you and the beacon, right? And so we had introduced the idea of correlation to be able to think about that. So correlation is a word that, how many people have heard the word correlation before coming to 16A? If you were following any of the election-related news, right, people might have said, like, such and such precinct is reporting, or such and such county is reporting certain kind of polling, and you've probably heard things like, oh, this is heavily correlated with something else, right? Certain maybe voter demographics are correlated with certain voting patterns. And the correlation that is being talked about in these kinds of contexts, in the context of the election or otherwise, is exactly the same correlation that we just defined in class yesterday. And not yesterday, Tuesday. Yesterday, actually, I was in Phoenix at a conference called Informs, giving a talk about some of the work I'm doing, actually with some Berkeley students. And if I have time at the end, I figured I might show you a little bit of that presentation, because one of the things that we were doing there was actually using correlation to understand different demographics and try to understand some of the issues in Alameda County itself. So if I have time at the end of class, I'll try and spend 5 minutes just showing you a completely different use of correlation than the one that we're going to be doing in the rest of class today. But let's pick up now where we left off. So does everyone remember these transmitted and received signals? We were sending, the transmitted signal was 1, 2, 3, 4, 1, 2, 3, 4. The received signal was shifted by something. So at 0, you were receiving 3, 4, 1, 2, 3, 4, 1, 2, so on and so forth. And what we were trying to do is we were saying, well, if I have this received signal R, I want to try and figure out which shift of S is actually the best shift that is closest to R, right? I was trying to figure out how do I minimize this error between them. And I was denoting shifts by this S underscore K last time, but just for consistency with the notes, I'm going to actually shift to having the shift be denoted as this superscript K with these brackets around it, right? So this just means the signal that is shifted by K. So if, for example, my S vector is the following, it's S0 all the way up to Sn, then S of K is just S0 is at the kth position. And this should be Sn minus 1. Sorry. And then there's Sn minus 1, Sn minus K minus 1, and this should be Sn minus K. Right? So this is just the shifted version that we're thinking about. And because I went over this a little bit fast, I'll go over it again. So we defined this vector E to be R, the received vector, minus Sk, right? And we want to minimize the length of E and how do we want to minimize the length of E? We want to find a K that minimizes the length of E. And sometimes when you're writing this in terms of an optimization, you write this out in a shorthand form where you say min over K. So what you're varying is K. K is the shift, right? And different shifts will give me different vectors. So maybe this shift gave me this vector, some other shift gave me some other vector. This might be Si. Maybe some third shift gave me some third vector. This might be Sj. And I want to figure out which of these shifts actually brings me the closest to the vector R. So I'm going to be able to vary over these shifts. So I want to find the min over K, and I want to find the smallest length of this error vector E, right? This is the error vector E. And instead of minimizing just the length, we're actually going to look at the squared length, just because it's easier computationally. And if you find the smallest squared length, it's the same as finding the smallest length, right? There's no difference between that. And then we said that, well, we know that this is just the same as R minus Sk squared. And we can write this then as this inner product, right? I can write R minus Sk transpose times R minus Sk. Again, we want to find this Sk, right? Sk is what we want to figure out. And then we can use the distributive property to write this out again. So we get R times R minus R transpose times Rk transpose times Sk. And then we have these two terms, minus R transpose Sk, and we have minus Sk transpose R, right? We have these terms. Yeah? This term should be plus, yes, thank you very much. right? Because, yeah, we're squaring these two things, so we remove that. Okay, everyone with me till here? And remember now, what are we trying to do? We're trying to find a k that minimizes this quantity. When I change k, does the inner product of r with itself, which is just the norm of r, squared, does this change when I change k? Nope. What about this second term, which is sk times, sk transpose times sk, or the inner product of sk with itself? Does this change when k changes? It doesn't, right? Because regardless of how this shift is, the norm of this is still the same. It's just the sum of the squares of this. So this is also the same. I can just write this as the norm of s squared. And what about these two terms? These two terms do change, right? Because my r is this guy, r naught, r1, all the way up to rn minus 1. And the pairwise mapping of these guys is different based on which k it is. So like, if depending on k, r naught is mapped to sn minus k. There is a dependence on k here. But what did we identify about these two terms? We have the inner product of r and sk. This guy is just equal to r sk. And this guy is just equal to sk inner product r. And these two are equal to each other, right? So these two terms are exactly the same. Does everyone see that? So I can just write this as minus 2 times r sk. And so when I'm looking now at my task of minimizing the length of this vector e over these k's, can I minimize this by changing r? R is fixed, right? K doesn't affect it. Can I minimize this by changing s? Nope. So what is the only thing I have left? I can only look at this guy, right? And so, remember here there's this negative sign. So if I want to make this, the quantity here, small, and it's equal to the negative of something, what can I say about what do I want to have for r sk? I want to effectively maximize this over k, right? I want to find that shift that has the largest inner product. Because if I make this large, the negative of it will be small, and so I'm effectively minimizing the length of my error vector. Is that clear? Okay. So now that we have this and we understand why we're thinking about correlations, right? We're thinking about correlation to think about how far apart these shifted versions are from what we actually received. We want to now move to thinking about certain other ways of thinking about correlation and inner product, just because it's going to be helpful to us as we go forward. So here, I'll try and keep this up here. Is this visible? Yeah, okay. And talk about this geometric interpretation. So we have this picture. Keep that in mind. I'm not going to redraw it. And we want to show that intuitively sk dot r should this guy, we want it to be basically larger if sk and r are close, right? If this angle between sk and r is small, we want this product, this inner product, to be actually larger. And so let's think about this in the 2D case, in the 2D geometric case. And so let's consider two vectors. Let's consider a vector, let's say these are our basis vectors here. And we have some vector, let me call it, this is some vector v, and this is some other vector w. And let's say w has angle theta w here, and v has angle theta v here. So now, can I use these angles to say something about my vectors? Let's say my v is actually equal to v1, v2. I can rewrite this in terms of this theta v, right? Using trigonometry. And I can say that this is equal to just the norm of v times cosine of theta v, and the norm of v times sine of theta v. This is just coming from standard trig, which is if this is theta v, and let's say this has some length L, then this side is L sine theta, and this is L cos theta, or theta v in this case, since we have this theta v. Right? Basic trigonometry gives us this. Everyone with me here? Because here the y component of this is just this side of the triangle, the x component is just this side of the triangle. What about w? If w is w1, w2, I can write this also as w cos theta w, and then the norm of w sine theta w. So what happens now if we consider this inner product of v w, which is equal to really w v? Just take a minute and write this out in the trigonometric coordinates that we've just found. Just do this calculation. Remind yourself of what the inner product is. If you've forgotten what the inner product definition is, ask your neighbor. Okay, how many people know what the inner product of this is? Just doing the algebra out. How many people don't know? Okay. So, does someone want to call out what you would do? Inner product is just multiply the first components, multiply the second component, so on and so forth, right? So I have just v1, w1 plus v2, w2. Is that right? And I can write this out further as the norm of v. I'm just going to substitute cosine theta v, norm of w, cosine theta w, plus norm of v, sine theta v, times norm, of w, sine theta w. Sorry, the handwriting got small here. But does everyone see this? Oops. No? No? And I can now pull out this norm, so I can have V, W, and I can write this as cos theta V, cos theta W, plus sine theta V, sine theta W. And now we can apply a trig identity, right? This is like the sum product rules that you've seen, right? So cos theta 1, cos theta 2, plus sine theta 1, sine theta 2. This is related to the cosine of the difference of the angles, right? If you don't remember how to derive this, go back and draw out a right angle triangle and use the trigonometric rule. So you can rederive this property in case you've forgotten it. So you have V times W times cosine of theta V minus theta W. Right? I'm just using this trig identity. But now this is telling us something very interesting, right? On this picture, what is theta V minus theta W? Alternatively, theta W minus theta V, right? Because cosine doesn't care about the sine. This is also equal to V W cosine of theta W minus theta V. What is this angle? That's exactly right here. Right? Do you see it on the picture? Theta W minus theta V is exactly what I've drawn in blue here. And so, if I think about this inner product, right? What do the values of cosine go between? What is the largest value cosine can take? 1. What's the smallest value cosine can take? -1, right? So I always have this. And when does cosine theta equal to 1? When theta equal to 0, right? Cosine of 0 is equal to 1. And cosine of pi by 2 is equal to 0. So, now, if you think about the angle between these two vectors, as the vectors get closer and closer and closer together, what is going to happen to the value of the inner product? It's going to get bigger and bigger, right? Because cosine is going to get closer and closer to 1. This term is going to dictate that. And what is going to happen as your vectors get closer and closer and closer to being at 90 degrees to each other? This inner product is going to go to 0, right? These are the two extreme cases that you're going to be coming up to again and again and again. And now if we think about, we're at 90 degrees, what happens now as your vectors become, okay, I can't draw that way, but my hands don't go. But do you see what I'm doing? If they're one vector is this way and one vector is this way, what's going to be the value of the cosine? -1, right? So you're saying that, here, their inner product is 0 when they're 90 degrees. When they're exactly aligned, the inner product is as high as it can be. And so by looking at the magnitude of the inner product, you can figure out actually how these vectors are directionally aligned. And this is a property that we are going to, keep coming back to over and over again. So I had a question from a couple of people last time after a lecture, which is something about, if I wanted to make the inner product big, is it just the direction of the vectors that matters? There's two other things that are mattering here, right? Which is the norm of the vectors themselves. But in the sense of directionality and in the sense of angles being close to each other, does changing the length of the vector actually change our angle? It doesn't, right? So would it be fine if I took any vector in the same direction and took an inner product in terms of figuring out whether the angle is big or small? So actually, when you'll be doing this in the real world or in the lab, instead of thinking about vectors of any length, you will actually be thinking about normalized vectors, or basically taking a vector and dividing it by the norm of the vector, so that what you have is a unit length vector. So the norm of the vector is always 1. And if the norm of the vector is always 1, then your inner product is always going to vary between -1 and 1 because of this. And so if you ever read the newspaper and see correlation numbers reported, they're always reported between -1 and 1. And this is because they're thinking about normalized vectors. And a normalized vector is basically a vector where you're dividing each of the elements by this norm of the vector. So, everyone with me here about how we're thinking about why we want to maximize this inner product and how that shows geometrically that these vectors are actually close to each other? Okay, so now that we have that, let's keep building, and we'll just talk about some properties of the inner product that you've seen before, but I just wanted to remind you. So the first one we've already seen, which is that if I have the inner product of x and y, this is equal to the inner product of y and x. The second one is that this distributive law, x plus y and z is equal to x, z plus y, z. Yeah, straightforward, like this we know. This is easy to verify. Third one, I think there was a question about this on Piazza or something. If I scale one of the vectors by alpha, that's effectively scaling the inner product. And an interesting fourth one, which is something maybe you have not thought about before. If I take the inner product of x with itself, this is always non-negative. Can you see this from the formula here? If theta v and theta w are the same, right, this angle is going to be 0. So this is always going to be 1. And if I have two x's here, this is just going to be the norm squared, which is always a positive number, right? Squares are always non-negative, which gives you this property. And the last one, which is that x inner product with itself, if this is equal to 0. This is true if and only if the vector x is the 0 vector itself. You can't have one vector, that when inner producted with itself gives you 0, unless that vector is 0 itself. But can you have two vectors which are distinct whose inner product will be 0 without each of them being 0? Right? You can, and this is something we're going to come back to in the rest of the lecture. But finally, since we've already done all of this, I wanted to share one really cool property about inner products with you, which is called the Cauchy-Schwarz inequality. Cauchy. This is something that will be useful, for example, for those of you who are taking CS70 eventually. But here, let's look at this. What do we know about the magnitude of cosine, right? We know that it's always going to be between -1 and 1, right? So if I take magnitudes on both sides of this, if I take absolute values, what do I know about this inner product and this guy? This product of these norms. If I take V, W, if I take its absolute value, this is always going to be less than or equal to let's do it this way. This is equal to V W times cosine of theta V minus theta W, absolute value, But the absolute value of this cosine is always less than 1. So this is always less than or equal to V W. So this is giving you an upper bound on the value of the inner product. If you look at the norms of the vectors, this is the largest that they can possibly be. And you'll see like this idea will build and build and build. And there's different forms of the Cauchy-Schwarz inequality that you will see in different classes. Depending on the context of the class, this might show up in a different form. Another way to think about the Cauchy-Schwarz inequality is to show that basically the sum of squares is always larger than the sum of individual pairwise product. And for those of you who might, be have exposure to something like CS70 already, you might have seen something like this. If you're interested in how this is equivalent to that, come talk to me in office hours. I'm happy to talk about it there. Okay, any questions about this? So the Cauchy-Schwarz inequality is basically giving us this idea of like the maximum value of what the inner product can be. But now there's the natural question, well, what about the minimum value, right? We know what the minimum value of the inner product can be. Let's think about the absolute value of the minimum. Yep, sorry. Minimum value. What is the minimum? What is the smallest absolute value it can have? It can be 0, right? And actually, this is a very special case, and I'm going to define this notion of orthogonality using this. So, two vectors v and w are orthogonal if v and w inner product is 0. And orthogonal is basically, it's capturing this idea of two vectors being perpendicular in 2 dimensions, right? Except that this is actually something you can generalize to more than 2 dimensions. So this is true in 3 dimensions, this is true in 4 dimensions, this is true in 5 dimensions. We will think about vectors as being orthogonal when their dot product is 0. So in 2 dimensions, like some vectors that you have seen that are orthogonal are, let's say, 1, 0, 0, 1, right? Our standard basis vectors. These are orthogonal. You've seen this. What about the vectors 1, 1 and 1, minus 1? Right? 1, 1 is this guy. 1, minus 1 is this guy. And if you take their inner product, what is it? It's 0, right? So we've actually already played with these ideas. We just didn't call out this label of orthogonality. So nothing really different or new that's happening here. But with this now, we can actually move to defining something that is very important and cool, which is the idea of a projection. Or sometimes you might hear people also call this an orthogonal projection. They mean the same thing. But let's say we have a vector A and a vector B. And someone asks you to project A onto the subspace spanned by B. So it's like saying, well, I really want to move along this vector A, but let's say I'm only allowed to move in this plane here, for example. If I'm only allowed to move in this plane, but I want to get as close as I can to this point, where should I move to? That is the point, that is the projection of this vector A onto, let's say, the subspace of this plane. So we are going to talk about projections here in the context of just the projection of one vector onto another. But you can easily generalize this. If we have time in the class, we'll talk about it. To thinking about projecting a a vector onto a general subspace. This is one notion that will quite easily generalize. So let's say I have, again, these two vectors. I have some vector b, and I have another vector a. And so basically, I want to say, well, I want to move along b. I'm only allowed to move along b, but I want to get as close as possible to a as I can. Right? Intuitively, or even based on the geometry that you've studied so far, where are you going to walk? Are you going to walk in this direction? No. Are you going to walk in this direction? Yes. And when are you going to stop? Are you going to keep going here, 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 here? You're going to stop around here, right? Seems like the closest point. So, turns out that you will know this from triangle inequality, that this is actually the closest point where this is perpendicular. But we're actually going to prove this and derive this in kind of a linear algebra way. So what we want to do is we want to say, I want to find a w and maybe not a w, let's call it a vector u and a vector z such that this guy, this vector here, is u, and this vector here is a vector z. So I want to find u and z such that u plus z gives me the vector a, and 2, I want u to be in the same direction as b, right? So u is in the same direction as b. And what's another way of writing this? How can we write this mathematically? The fact that I want u to be in the same direction. That just means that u is in the subspace spanned by b, which means that for one vector, how do we represent a subspace? Just by a scalar, right? So that just means that u is equal to alpha times b, right? If u is in the same direction as b. And the third thing I want is I want z to be orthogonal to b. And we just defined orthogonal. This means that the inner product of z and b is equal to 0. Right? We want to find these such u and z. So, really, what is unknown here? What is given to me? I know a, and I know b. And what is unknown? U and z, right? But given that I know u plus z is equal to a, as soon as I find out one of the two of these guys, I can immediately find out the other just by subtraction. So I really just need to find one. And so I'm going to focus on finding unknown u. And because u is just this scalar alpha times b, the focus is really going to be on finding unknown alpha. So what I'm trying to do here is I'm trying to use this idea of inner product to think about how I can decompose a vector into a vector in a known direction and the other direction that is completely orthogonal to that known direction. So if we want to do this, how could you go about trying to even find this alpha? Maybe take a minute and think about it. Like talk to your neighbor, try to play around, see how could you compute such an alpha given the properties of inner product that we've looked at so far and what we're trying to do. Just take a shot. Remember, we want to find the unknown alpha in terms of what we know, and what we know is A and B. Okay, how many people have some idea? Okay. Maybe we can work on it a little bit together and see where we get. So, the way I thought about this was, well, what do we know? I know that I want to find both of these, but I don't want to deal with two unknowns. So the first thing I'm going to do is I'm going to write z is equal to a minus u. Right? And then I know that I want the inner product of z and b to be equal to 0. So then I'm going to say z inner product b is equal to 0, which is the same as saying a minus u inner product b is equal to 0. But now we can apply a distributive law, right? So this gives me a inner product b minus u inner product b equal to 0. So here now, when we look at this equation, what part of this equation has fallen into our known category? This a inner product b is something we can calculate, right? We know this because we know a and we know b. So what is left is something that is kind of unknown. It's this u inner product b. But can we write u in terms of b? So you get a inner product b minus alpha b inner product b. And now we can use the other property to say that a inner product b minus alpha b inner product b is equal to 0. So what does alpha equal as a result? I can now write alpha as basically a inner product b divided by b inner product b, which is just the norm of b. Whoops. So now we have basically this alpha in terms of quantities that we entirely know. And so now how would you write u in terms of b? U is just a b times b. Remember, inner product is a scalar, this norm is a scalar, and so these two are vectors, right? The dimensions of this check out. And remember back in the first module when we learned about change of basis, right? When we learned about change of basis, we said, well, let's say I have a vector, but I want to express it not in terms of the standard two vectors, but I want to express it in terms of some other vectors. Like how much would I walk along, let's say some vector b and then some other vector, let's say z, to get to my point A. In this case, if I had to, for example, think about, can I express vector A in the basis given by vector b and vector z? This projection is exactly what I want to do. I want to say, what is the component of A that is along B? And then, what is the remaining component? Right? The component of A that's along B is u. The remaining component is given by the z. And so u plus z is equal to A. If I had to express A in the basis given by B and z, I would have basically the first coordinate in the b direction would be given by this. And what would be the second coordinate in the z direction? Think about it for a minute. It should be fairly, it's basically the answer to this is connecting up change of basis with projections. If I wanted to express A in the basis given by B and Z, what is the coordinate of A along the Z axis? First, what is the coordinate of A along the B axis? That is given by this, right? Because remember, what does it mean to represent a vector in a certain basis? It says, first, how long do I walk along vector 1? Then, how much do I walk along vector 2? Right? So, I know how much I need to walk along this vector B. It's given exactly by this. We just computed it. Now I need to figure out how much I need to walk along this other vector Z. Yeah, how many people think they have the answer? How many people need a hint? Okay, so let's do this. So let's say that find coordinates of A along basis given by B, Z. Okay? So, how did we define the Z vector? We defined the Z vector exactly as this vector, right? We defined the Z vector as A minus U. So it's exactly this. So once I walk along B up till here, how many multiples of Z do I have to go to get to A? Exactly 1, right? I defined Z to be exactly that. So if I think about these coordinates, I think exactly of A, B, and then 1. Because I just take exactly one step of Z, and immediately I get to A. And so if I was to now think about the projection of A in the direction of Z, what would I get? Could I do the same calculation again? Yeah, but I shouldn't. Why shouldn't I? I could just take A minus U, right? That would give me the same answer. So there's multiple ways of doing this. But I just wanted to show that all these things connect up. It's not like there's one orthogonality thing and one projection thing and one change of basis thing, and you have to remember all these different formulas differently. The point is to say that these are all connected ideas, and if you remember these interconnections, hopefully things will get easier. Yeah, question?
Doesn't the projection, so when you use projection as a change of basis, doesn't that only work for orthogonal basis?
Yes, it will only work for orthogonal basis, and this is why here you do have an orthogonal basis, and this is exactly what we're going to come to in a couple of lectures, is how do you compute a basis for a space, right? Here in this case, we only gave you B, and we said, if I tell you first walk along B, what's the second direction you can choose so that then you can get to A? An easy direction to choose is the direction Z. Okay, so that was just a small connection to something we've done before. Let's keep going. And finally, think about, let's come back to the locationing example and how does all this actually connect up, right? So now we understand a couple of things. We understand orthogonality, we understand projections, we understand inner products, and why they bring us, why they indicate similarity. So if we're now connecting this back, yep. So we're here again, and remember we had this beacon, and it was sending stuff, and it had this periodic song, And then you had this person with their antenna, and you were trying to figure this distance d out. And just to recap, right, we have the beacon sends this periodic signal. Then you use correlation to find the best aligned shift. This gives you the transmission delay. Which then allows you to compute the distance, right? And what we talked about was really these periodic signals. Periodic signals. And we defined this correlation in terms of the period. And so, just so that, you guys are aware of all the different ways we can write this. So we talked about correlation n between, let's say, R and S. And we defined this as equal to I going from 0 to n minus 1. And we said, let's look at basically the inner product of R with a shifted version of S, right? Everyone remember this? N is the period of the signals. But we can just rewrite this. Oh, and what did I miss here? I should write an index here, right? This should be correlation at element K. But I can also write this just as an inner product, right? This is just R inner producted with S shifted by K. Remember, I'm writing correlation here, and when I'm writing a correlation, the order of the arguments matters, because which of the two vectors I'm going to do the shift on depends on the order, right? Here I'm shifting the second vector. So when I write it as this inner product, don't get confused by the fact that here you can interchange the arguments and here you cannot. Right? Here I'm writing it as this inner product, but I'm writing it as a shifted inner product, and I've shifted S, which is the second term here. So it's easy to switch this up, and I've seen a lot of people get confused by interchanging the order of the arguments. Please remember to be careful about this and don't do that. But we can also write this in another way. We can write this as a circular correlation. And it's basically the same thing. It's just that instead of thinking about this infinite periodic signal, which keeps repeating, we can just think about it as just one period of the signal. And I can write it exactly in the same way, where I have this sum again from I is going from 0 to n minus 1, R of I. And if you look at the notes, the way it's defined is S of I minus K n. And what is this n here? This is saying that instead of thinking about this infinite repeating signal, you can just loop things back. So remember here, this is the picture we had last time. Remember here that y of 0 is equal to y of 4 is equal to y of 8 is equal to y of minus 4, so on and so forth, right? So let's say here my I minus K gives me a number that goes outside of my period. I can just map it back into something that is within my period. And that's what this kind of mapping operation, this circular mapping operation is doing. So if you think about it, you can just think about for period 4, for example, you have y of minus 4 is equal to y of 0 is equal to y of 4, so on and so forth. And you have y of minus 3 is equal to y of 1 is equal to y of 5, and so on and so forth. And so basically, whenever I get a number that's outside my 0, 1, 2, 3, I can always map it back in. Does everyone see how, because this signal is periodic, I can always represent this? I can take whatever number there is and map it back to some index between 0 to n minus 1. So, again, this is something that I've seen a lot of people get confused with, is how does this wrapping happen? If you get confused with it, just try to draw out a picture. Do it for something simple with like period n, n is equal to 4 or 3 or something small. That'll help you get unconfused and go on. But like, these are two little notational things that people trip up on, so just try not to get confused accidentally. And then we saw that we can actually represent this as a matrix vector multiplication, right? So instead of like computing each of these inner products one by one, which is a lot of vector multiplications, I can just do them in one big stack by writing out what we defined as a circulant matrix, S0, S1, all the way up to Sn minus 1, n minus 1, S0, Sn minus 2, S0, and here you will have S1. And I can write this as R0, R1, Rn minus 1. So I'm just basically stacking these shifts of my vector on top of each other to get this circulant matrix. And whether I want to calculate this being called the periodic correlation or the circular correlation, I can use this trick to do it in one shot. Most of the times in this class, we will be dealing with these circular correlations. That's what you're going to be doing in the lab. But just because, there's so many different applications of correlation, I wanted to just introduce a second notion of correlation, which is just a linear correlation, which is almost exactly the same, just slightly different. So here I can define linear correlation. And let's say I have two signals. Let's say I have minus 1, 0, 1, 2. Let's say I have 1. And let's call this, let's say, y of n. Let's say I have minus 1, 0, 1, 2. I have 1. And let's say now I want to figure out this correlation of x and y. In this case where I have these x and y given this way. And x and y are not periodic. But remember, what do we want to try and capture by the idea of correlation? We want to capture similarity, right? And so if you were to intuitively look at this and say, what shift should I look at of y to be able to match up with x? Like, do they match when there's no shift at all, when I align them at the zero index? Is that the best match that you think? Where would you want to do? You would want to push y forward by 1, right? Because you see that these guys align well with these guys. And so linear correlation actually captures this idea. So correlation of these two vectors, x and y, is just the following, where now I'm going to sum from minus infinity to infinity, and I'm going to think about x of I, y of I minus k. And now I can compute the correlation of, let's say, x and y at shift 0. And at shift 0, this is just 1 times 1 plus 2 times 1 plus this 2 times what is here? This is just a 0. So this is just gets a 0. And this is 3. But now if I compute correlation of x, y at shift 1, what do I get? I get a 0 for this guy, so I get a 0 plus a 1 plus a 4, which is equal to a 5. So I can do exactly the same thing. I've done nothing but plug this into here. It's exactly what we were doing for periodic things, except now there's no wrapping back because our signal itself isn't periodic. So think about these two signals just like moving, like one is moving like a train along the track of the other. And you want to find the point at which they're most aligned. Think of it as like a jigsaw puzzle, right? You're going. When they're most aligned, they're going to slot in. And you're going to get this high correlation. And a lot of times when you'll see, for example, in machine learning applications or when people are talking about correlations in trying to do statistical analyses, they're often thinking of something like a linear correlation because you might not always have this nice periodicity. When you can engineer the signals, you get to do that, but you don't always have that. So you probably saw this a little bit in discussion yesterday, and you'll see it a little bit more in the homework, but I just wanted to introduce it so that you're aware that, you know, when someone says correlation, it's not always necessarily a periodic signal. Okay, so that's that. Finally, we had to connect up all of these pieces together, right? Because we now know how to find the distance from one beacon, but really what we said was we wanted to do this with multiple beacons, right? We have this one person here, and oh, sorry. Thank you. Yes, please remind me if I accidentally forget, because I don't notice when I'm looking down. I have let's say A, B, C, DA, DB, DC. And I really want to figure out the distances from all of these different beacons at the same time, right? And we can't really say hey, by the way, satellite 1, kind of stop, because I'm busy talking to satellite 2 right now. You can't really have these signals stop and come and talk whenever you want. So you have to be able to deal with processing these signals all together. And what we have now been building up to using orthogonality and projections and inner products is going to come in incredibly handy to handle these multiple beacons. So let's say now I have some received vector R, and because now I'm receiving signals from 3 different beacons simultaneously, what am I going to receive at my receiver? I'm going to receive the sum of all of these signals, right? They're going to superimpose, which is something you might have heard of before. So let's say I have a signal SA coming from this beacon, and let's say it arrives at a shift of dA, so there's a delay A. And then I have a signal SB, which arrives at some delay B, and SC that arrives at some delay C. Now, what am I going to do, right? Remember, when we had just one beacon, we just got this much. And then we could do our inner product to figure out what dA is. But now, we don't have that luxury, right? We have this other interference that's coming in. And we need to be able to figure out a way that we can understand the delay from satellite A, even though satellite B and C are both transmitting to us. So, what are we going to do? Our standard trick would be to say, well, let's look at this received vector A, and let's take the inner product at some shift k, right? And we want to find that k that maximizes this inner product. And that will be the best when k is exactly equal to dA. So what if we do exactly what we used to do, and we'll just write this out. SA at dA plus SB at dB plus SC at DC. Inner product SA with shift K. Right, this is what we got. We can use the properties of inner product to then write this as SA of dA, inner product with SA at K, plus SB at dB, inner product with SA at K, and plus SC at DC, inner product with SA at shift K. And now, what would I ideally want if I wanted my strategy to just keep working? And remember, we're the engineers. We get to design the signals that are going to be sent out by the beacon A, beacon B, beacon C. Ideally, to make this problem look as much like our old problem when there was just one beacon, what would I want to have happen to these two terms? Yeah? Yeah? They go to 0, right? Ideally, we want to make these disappear. We want them to be as though they never existed. That would be great, right? Because then all of this stuff that we've built up for one beacon, we could just reuse right again. So, what do we know? So if we want them to be 0, what is that saying about this inner product? This inner product is 0. What do we know about two vectors when their inner product is 0? They're orthogonal, right? So what would we want the signal sent by beacon B to be compared to the signal sent by the first beacon? We want it to be orthogonal. What about the signal from the beacon C? We want it to be orthogonal. And this is actually exactly how these codes are designed. On the homework this week, what you're going to be doing is you have a problem that you'll work out actually using real gold codes, as they're called, which are actually the codes that are used, for example, in cellular communications to orthogonalize signals. So you have these different signals that are sent out. These are real, signals that are being used in GPS transmitters in your cell phones that are such that they are actually orthogonal to each other, yet they have, and you can actually decode this. Sometimes you're not able to get signals that are exactly orthogonal. Sometimes you'll get some small inner product, very, very close to 0. But if this term is much, much larger than these two, and these two are almost orthogonal or almost close to 0, this is something that actually kind of works out as well. So basically you want this guy to be large, and you want these other guys to be quite small. So this is something that you'll explore more in the homework and absolutely a lot more in the lab, but this is the key idea of what is exactly going on. And so because we design these signals carefully, we can actually use exactly the same strategy we used for one beacon, even in the case of having multiple beacons. So now finally we're coming very, very close to finishing all of this up, right? We now are able to get these distances. We're able to get them even when there's multiple beacons. But the question is, how do we actually find out what our location is. Actually, maybe I'll save this picture so I don't have to draw it again. If I wanted to actually figure out what my location is from this, let's say I gave you this dA, d was the shift, so let me call this distance something else. Bad notation. Let me call this d1 is distance, d2 distance, shift, d3. So let's say I'm distance d1 from A, d2 from B, and d3 from C. How do I actually figure out what my location is? Let's say my location is this unknown vector x. Oh, sorry. Sorry, thank you. Appreciated. Okay. So I'm distance d1 from A, d2 from B, d3 from C, and my unknown vector, my location is x. So how do I actually figure it out? Like we did it yesterday or Tuesday, kind of drawing these circles, right? But it's a bit of a tedious way to actually figure things out. Is there a way we can computationally do this? Can we design an algorithm? And this is the algorithm that I'm going to try and finish up class with. So let's say the location of this beacon is A, and I know this. Location of this beacon is vector B. Location of this beacon is vector C. So I can write, let's see if I keep this here, and maybe right here. Maybe you can see. Okay. So now I know that x minus A squared is equal to d1 squared. I have x minus B squared is equal to d2 squared. And I have x minus C squared is equal to d3 squared. Right? And what have we done so far in this class many, many, many times? We have done systems of linear equations, right? Basically, all through Module 1, whenever anyone asked me a question, I said, what is the one algorithm you've learned? There's only one algorithm. We kept doing that algorithm, right? So what do we want the answer to this question to be? We want the answer to be Gaussian elimination. But what's the problem? There's squares floating around, right? We're suddenly in quadratic land. We don't have these nice linear equations that we're used to. And the question is, can we do something about that? So if I expand this out, I get this x squared minus 2ax plus a squared right? I get three equations like this. X is my unknown. Does the square on the A bother me? No, because A is a known quantity. We know A squared. The only thing that bothers me is x squared. So, can I do something to get rid of this x squared? So I have these two equations, and they have this x squared, and I don't like the x squared. What do I want to do to these two equations? Oh, yes, thank you very much. That was a typo. Very good. Thank you. This was a typo. Everyone see that? What do I want to do to these equations to get rid of this? Subtract them. So what do I get if I subtract them? I get basically that 2 times this inner product What do I got? I got linear equation. Quadratic term has completely disappeared. So what do I want to do with my third equation? I'm going to do the same thing, right? I'm going to subtract equation 1 from equation 3 as well. So this is 2 minus 1 gives me this. 3 minus 1 gives me the same thing, just with b replaced by c. And now I have two linear equations. And in this two-dimensional example, how many unknowns are there? 2. So I can write this out in my usual way that I enjoy writing. So I have this x inner product b minus x inner product a. Can I combine these? Can I use the laws? Can I write this as x inner product b minus a? So I can write this now as b minus a transpose c minus a transpose times x is equal to, just copy these terms into here. I have a system of linear equations. What is the answer? Now you can use the favorite algorithm, the only algorithm, and you can solve this once again using Gaussian elimination. The interesting thing is that you will finally, next class, be learning a second algorithm. So now, when I ask you what's the algorithm to use, you will have two options. But since we haven't learned that yet, right now the right answer is still Gaussian elimination. Next class, we'll be talking a little bit about the least squares algorithm, which helps you actually deal with the fact that sometimes here you will have noise. What we're talking about here is called trilateration. This is what this algorithm is called. Okay, I have like a couple of minutes left in class. So for those who are interested, I was going to show you some of the other uses of correlation that we might actually be able to do based on this talk that I gave yesterday. For those of you who are interested, you can stay. For people who aren't, up to you. But this is a project that I was working on with a couple of these students. So these are actually all three people. Probably some of you know them. They're all undergrads here at Berkeley. And what we were thinking about is how to think about putting emergency rooms in the Alameda County area. This was motivated by actually the fact that people have been talking about closing the Alta Bates Hospital. Some of you might have actually visited there. But one of the things we were thinking about in terms of actually trying to figure out where we should make these locations, where we should put this, is thinking about, equity across different kinds of demographic groups, different kinds of people in the state. And one of the things we wanted to make sure we didn't do, for example, was like privilege a certain group over another group. So what if you wanted to say that I wanted to have, equal access for people regardless of their income level, or regardless of whether they're covered by health insurance, or regardless of what ethnic or racial background they identify with. So on the way to doing this, there's a lot more going on this project. But what we did here was we're showing here, this is population centers in Alameda County. And what every dot is representing is a census tract. And the color of the dot represents, on the top plot, the fraction of people in that census tract that are above the poverty line. So you can see the fraction that, like all the dots that are very, very red or very gray, have almost everyone in that census tract above the poverty line. But then the green and yellow dots are having people that have, only 60% of people that are above the poverty line, or maybe in some cases only 70%. That's what the green and yellow dots are. And what the bottom plot is showing is that look at the population and then let's look at the number of people in the census tract that have health insurance. And you can see that there's a lot of similarity between the pattern of the red and the green dots in both cases, right? And the natural question is, well, what is the correlation between these? And actually what we were doing was actually exactly calculating the correlations across different demographic features, which is what is being shown in this plot. And when you correlate a vector with itself, you always get 1, which is why the diagonal is all 1s. But if you look at the correlation between, for example, people who have health insurance and people who are above the poverty level, you get this green 0.64 because there's a high correlation between these two populations. A lot more to be, talked about here. I just wanted to show you a different application of correlation, something that is, very current, very relevant, something I'm thinking about a lot right now. See you next week.
So regarding in this